Okay, welcome to our second video. This is in kind of our first set of kind of 2 weeks where we're just doing some pre-calculus review. Today is kind of a hodgepodge of topics. We're going to talk about operations on functions, domain and range, as you can obviously see from the title here. We're just going to focus on, some like the nitty-gritty details involved in certain elements of calculus. We're going to talk about interval notation. As I scan through the notes here, we'll talk about how to represent things on number lines or set notation, different ways of writing things. We'll talk about different types of functions, including the terminology about domain and range. Pardon me. More notations. We'll talk about all sorts of different types of functions, including a new thing you probably haven't seen before called the piecewise function. Definitions including continuous and discontinuous, a brief talk about transformations and how to operate on functions, including compositions and finding the domain of composition of functions. And that's kind of our main setup here today. So it's kind of a hodgepodge in a way. It really is. Like, it's not overly cohesive. Just a bunch of little definitions and terminologies, most of which I'm going to expect you to have learned in 30-1 at some point. So even before 30-1. So, okay, well, without further ado, let's get started. So, first thing I want to talk about here is what you can read. We need to know the term interval notations, and it's used to describe solution sets in something called inequalities. And going forward, I better make sure everybody understands what an inequality is. Inequalities are represented either by these symbols, the greater than or less than symbols, or the greater than and equal to, less than and equal to symbols. These ones right here. An equality involves an equal sign. An inequality is one of these four things here. And it usually means that you have a range of answers. For example, if I told you that x was greater than 2, then there's actually lots of answers. You could have 3, 4, 5, 6, 17.3, 42 million, 17 pi over 2. Anything that's greater than 2 would work. So 2, 1, 0, negative 1, those don't work. So if there's a range of answers, then we need interval notation. Before I go further, I should clarify the verbiage. Range, though, specifically refers to y values, the output values. In a way, what we're actually looking for is a domain, which is a similar concept, just a different word. A domain is, well, what x values are valid in case there's more than one that is valid. So, yeah, let's move on here. I think you guys can read that. So here's the two main ways that we represent a range of answers. Again, a range kind of being a different word for the domain, what x values are valid. So here's one way you could say that x is between -2 and +2, and you put it in this sort of funky notation. I usually don't worry about the x with the bar and the y element reals part as much. Like, sometimes I just ask kids for this bit here. But in case you want to know kind of how this technically works, this means that your answer is x. This line is supposed to be a notation for the words such that. At least that's what I've heard it called. So this is x such that x is between and equal to -2 to 2, with the restriction that x better be a real number. So that means that it doesn't necessarily have to just be it doesn't just have to be integers or natural numbers. It could be a decimal number. It could be an irrational number. It could be a fraction. This just kind of limits things. If it said that it had to be x as an element of, like, say, the natural numbers or the integers, that changes things. But this is a pretty traditional way of writing things. Like I said, I'm a big fan of just sticking with this bit right here. I feel like it's sufficient to meet our needs, but that's hopefully something you're familiar with. Another way of writing it would be to draw it on a number line. This is something that we will be doing, by the way, going forward in calculus. It's an important skill to just have a way of representing a range of answers, or a domain of answers, if you prefer just to think of it as x values as inputs. So based on this could be written in the same thing. This is -4 to x to 5, but on this one here, I have the or equal to sign, and this one here I don't. An open circle means you don't actually get to include that value. A closed-in circle means you do get to include that value. So hopefully you know this. There's a third way you need to know, and hopefully you do, because this has been tested on the diploma exam a lot more recently, including to my frustration, where I feel like it's been done just purposefully to try to catch kids who they know domain and range, but they've never necessarily seen this notation as much before. This is interval notation. And basically, it's written kind of like a coordinate pair. You know how, like, you write an XY coordinate pair where, like, 2 and 1, this is the x value, this is the y value. It's written in a similar sort of manner. It's written with two things right here, except the first number is like where you start, and the second number is where you finish. So if I give you -2, 2, it means the lowest number you can have is -2. The biggest number you can have is +2. A comma in between just to indicate, like, that it's between these values. And then square and round brackets basically refer to whether it's open or closed. So if you get to include 2 and 2 or -2 and 2, then use the square brackets. If not, use a round one. So as a shorthand notation here, this is a domain would have been 4 with a round bracket. Sorry, -4 with a round bracket, and then 5 with a square bracket. That's like the shorthand notation for being able to use interval notation. So hopefully you have seen this before. This isn't brand new to you, but it's something we need to know how to use. Indefinite intervals basically means, or infinite intervals, whatever, indefinite into infinite, basically means that it goes on indefinitely or to infinity. And so you have to use the infinity symbol. If it's just like x is greater than 2, you'd say, well, the lowest you can have is 2, and the biggest you can have is infinity. The note I have to indicate here is that if you ever use infinity, you always use a round bracket for infinity. That's just convention. So it's also possible that you can have a section here where I ask you where your values happen to be, and maybe there's like a gap. Let me give you an example of how this would work. Let's say that I gave you a graph like this. This is your standard cubic graph. And I asked you, where is this graph have an output, a range, let's say, where it's above 0? And if I were to highlight it, maybe you've done one of these before. Let's use yellow here. Right here, it's above 0. And right here, it's above 0. So then the x values, the inputs that would provide you an output that's greater than 0, would be from here to here, and then from here onwards. And that's kind of similar to what we have going on down here, where you could have, say, from 2 to 4, and then from 6 onwards. So what I need you guys to know is this symbol right here. It's a U, and the U stands for the word union. It's a very common mathematical symbology that gets used. Basically it just means that you can have from here to here, or often union refers to the word or in a way, or it can be from 6 onwards. So those are your possibilities. So hopefully that makes sense. Again, this is mostly just giving you some knowledge at this point here. There's nothing particularly doing. We're not doing anything with this yet. I'm just kind of showing you different possibilities. So, okay, more definitions. This is really a nomenclature kind of day where we're giving you verbs and adjectives and nouns and words we use to describe stuff, right? So hopefully you know the word function. A function basically is a rule that assigns elements in domains to range, and there's so many ways that those can be represented. I teach my 30-1s the concept of a vending machine, the idea that you input into a vending machine money, and then you press some buttons, which is kind of like what the function does. And then when you press those buttons, it outputs you something. So if I input the code A1, I get back a can of Coke. If I input the code B7, I get a chocolate bar. And so when I talk to my kids about domains and ranges, not everything necessarily is in the domain and range. In the vending machine example, the domain could be the code A7. Well, what if there isn't an A7 in the vending machine? What if it only goes up to A6 and then it goes B1 through 6? Maybe not every input is valid. If I try to type in the code AA532 and I let my toddler try to type it in, the machine says, error, I can't process this. So that's kind of a domain. It's what do you input. Traditionally, linear and polynomial and quadratic functions, usually everything's valid, but there are some things you can't use. For example, those of you who have learned about logarithmic graphs. Logarithmic graphs look somewhat like this. And over here in the negative x's, you can't actually input a negative. If you try to do the log of -2, that can't work because the input value of -2 is not valid. Just like the input to the vending machine of 3359A4, when my daughter just types in gibberish, it also doesn't work. So domain is what you input. Range is what you output. Range is what you can get back. So if you like the vending machine analogy again, I can go to the vending machine and I could get out a can of Coke or a can of Pepsi, but I can't go to the vending machine and get out a motorcycle because the vending machine doesn't have a motorcycle as one of the options. Right? Similarly, if I were to give you a graph of, say, a quadratic, say like this one here, and I ask you, where does the output equal 7 Well, if 7 is up here, if this is where the output is 7, you would then say, well, it doesn't, because the output doesn't get that high. So often we need ways of representing what the domain and range happen to be in terms of like their limits. So went too far there. So, I mean, this is a pretty basic example then. If I ask you to make x be your input, your domain, all you got to do is just plug in 5 for x. So it'd be 15 plus 4 means that your output is 19. So hopefully that's words you're familiar with. Domain, your inputs, which we represent with x. Your range, your output, which we either represent with f of x or y. And you will discover as we go forward in calculus that symbols and what we choose to represent things is really important, because as things get more and more complicated, we need to make sure we're clear on what's happening. And so sometimes it's better to go with f bracket x rather than y. And I'll show you some reasons why when we get to it. But so many kids, they ask me when they're in like grade 10 and grade 11, why can't I just write y all the time? And it's a good point. You could write y, you could write smiley face, you could use a star if you want, but there's actually some logistical reasons as to why f bracket x is actually sometimes a preferred notation. So, but we'll get there. So, okay, when you graph a function, the graph of a function then, seems kind of silly to define it, but the graph of the function would then be all of the ordered pairs defined by x and fx, or like essentially x and y. Right? If x and y is a point on your graph and they can be plotted, then that makes the graph. So if you have a graph and it goes wherever, right? All of these points should be an xy point. There should be an xy point here. There should be an xy point here. There should be an xy point here. And that's what a graph would be. Well, it seems silly to define it that way, but the graph of a function, f of x, with a domain of d, so whatever is in the domain, x is something that you can actually have an x here. There's not like all of a sudden it stops and then it picks up again. If x is valid, then all these points should be able to be plotted. Here's some functions that hopefully you're familiar with. If you're doing this at the same time as 30-1, I mean, it's going to be a challenge because you're learning things a little out of sequence, but we'll make it work. Linear, hopefully you're familiar with that. It's a basic straight line graph. Quadratics have a parabola shape. Polynomials, usually they, depending on the degree, look something like that. Radical graphs, radicals are square roots. They typically have this sort of shape to it where they don't actually have negatives allowed. Rationals usually involve having some sort of vertical and horizontal asymptote. Exponential graphs also have restrictions to the range. You cannot have them in the negatives without transforming them. Logarithms are their inverses, yeah. And it involves flipping them over to the line x equals y. And they're very similar.
Randy Bonnet, please come to the office for a phone call.
This is the first time this has happened. As I make videos, I'll have to apologize if there's announcements over the PA system because sometimes that'll interrupt my videos. Where was I? Logarithmic functions. You can't have negative x inputs. Trig functions. You've got your basic sine and cosine type graphs. There's also tangent, which looks like this. If you've seen those ones before, with the asymptotes in there. These are the ones I want to focus on here, the composite and piecewise functions, because you may not be as familiar with those. I think I'm doing piecewise on the next slide here. I'll come back to composite in a second. So here's a piecewise function. It gets written kind of oddly. It basically is an if statement. Like if x is greater than 1, then we use this. And if x is less than 1, we use this. And if x is greater than 1, we use this. I mean, honestly, it makes a lot of intuitive sense. If it's 1, then it's an x squared. So let's see, 1, let's say it goes right here. It's an x squared graph if it's less than 1. So this would be your basic x squared graph. And normally the graph would continue up here, but it won't. Because at this point, then we're going to make it a 2x plus 5 graph. And a 2x plus 5 graph would have a y-intercept up here, it'd have a slope. I'm going to use make sure I'm clear on this. I should be using an open circle here, by the way, when I kind of draw it up that way. Sorry, this isn't my best graph ever. Hopefully this makes sense, though. Here you have a quadratic graph for the less than 1 version of it. And I've drawn a black dot right here indicating that this is what the value 1 includes. It's on the quadratic graph. But then on the linear graph going forward, I use an open circle because everything is up to this point, and then it starts again on the other side. So that's a piecewise graph. It's very straightforward. You just graph two different portions of it, and it may not necessarily be considered what's called continuous because of the fact that there's kind of a gap here. Hey, that's my next slide. It's fantastic. So if I were to ask you to graph some of these things and figure out whether they're continuous or discontinuous, I mean, basically the definition for right now is, does it kind of keep going? If it keeps going, even if it's piecewise, right, even if it does this, and then it restarts again here, there, that's continuous. If it does this, and then it starts up there, then it's not continuous. All right, so let's do a couple of quick graphs here. If I give you this x squared minus x minus 2 over x minus 2, hopefully you remember doing these in the past. This is actually x minus 2x plus 1 when you factor it over x minus 2, which means that it cancels, and it provides you a pretty straightforward linear graph, which may look continuous, except there will be a hole in the graph where x is equal to 2. There's actually a gap in the graph because this is your non-permissible value when x is 2. So this guy right here, this top one, would not be continuous because there's actually legitimately a hole in the graph. And if you've been shown on a graphing calculator how to look this up with graphing technology, it will show you there's actually ways that you can see that there is a hole there through the table of values or using solve functions. So if we try the next one here, if I ask you for the graph of 1 over x, well, 1 over x looks something like this. It's got your two different sections here where it's a reciprocal graph, and normally you can't use 0. On this one here, if it's 0 though, it says that you can have a value at 6. So it's almost like you have a graph where there's like it goes down, then it hits right here at 6, and then it comes down and over to the side there. And I mean, everything in the domain is valid, but this isn't really continuous in that same way, right? Because for it to be continuous, it's got to continue in one consecutive line. So if you could do this and then jump up to here and then go down, sure, that's continuous. But if I have to do this, stop, then draw here, stop, then draw here, that's not continuous. Wait, for the last one, it says that it's x if it's greater than 0. Well, that's just your basic linear graph, so that looks like this. And then it's a negative x squared when it's less than 0, which would look like this. Well, it actually so happens that these two things actually line up. I mean, imagine that you had two fingers. I'm doing this kind of visually, so you can't watch me do this, but imagine that you kind of took your two fingers and you kind of like move them towards each other slowly. And if they touched, then it's continuous. But like if you missed and like, one went over top of the other, then, then it's not continuous. That's kind of what's happening here is those one piece kind of comes and joins the other one. If they fit together just perfectly and they land at the same spot, well, then it's continuous. So this last one was, but these guys here weren't. Okay, next topic. You should know about how to transform a function, and all transforming works pretty much in the same way. There's kind of a pattern to this. You can have what's considered to be translations and stretches or compressions, depending on whether these values are either inside or outside of the function. This a value right here will make a graph kind of taller or shorter by compressing it depending on its value. This last value, if you like put a plus a d on the outside, it literally will just move the graph up. This one will move the graph side to side. And then this b value will like compress it in or out. So my arrows aren't really useful here. Let's see if I can make this better here. This a value will either make it smaller or bigger. And this b value will either make it go side, like squish it horizontally. Okay. Whereas the c value will just straight up move it side to side. And this d value will move it up and down. Maybe that notation makes better. This one does both. It stretches it up, like it's a stretch up and down. This is a stretch up and down. This is a stretch up and down. And this is like a translation side to side. You should be familiar with these. It should be one of the first things you hopefully learn in 30-1. For those of you who are doing it at the same time here, we'll practice this a little bit so you're familiar with it. But this is a way to manipulate a graph around a little bit. So. Okay, another thing you should know how to do is compositions of functions, where you add, subtract, multiply, divide, and then actually like replace one with the other. So let's do an example here. If I ask you to add these two functions together, I mean, as you add them, it's pretty straightforward. If you take x squared and add it to x squared, you'll have 2x squared. If you take 3x and add negative 2x, you'll just have x, and minus 4 add to plus 1 is minus 3. So you can add them to each other. You can subtract them. If I take g of x and subtract h of x, the x squared and the x squared will cancel. Minus 2 minus 3 will give you minus 5. 1 minus, oh, careful here, 1 minus minus 4 gives plus 5. You can subtract them. You can even multiply. Multiply is not going to be overly fun because you've got to FOIL this guy. But hopefully you can follow this. X squared times x squared, x to the 4. X squared times 3x is 3x to the 3. X squared times minus 4 is minus 4x squared. Minus 2 times x squared is minus 2x to the 3. Minus 2 times 3 is minus 6x squared. Minus 2 times minus 4 is plus 8x. 1 times x is x squared. 1 times 3x is 3x. 1 times minus 4 is minus 4. Put it all together, x to the 4 plus x to the 3. X to the 4 plus x to the 3 minus 9x squared plus 11x minus 4. There. That's what happens when you do f of x times g of x. Hopefully you guys are familiar with being able to do something like that. F of x divided by g of x. Let's just erase all this. Give me a sec while I erase so we can make some room here. There we go. G of x divided by h of x would be this guy over this guy. This will be x minus 1, x minus 1. This will be x plus 4, x minus 1, and something cancels. Right, so hopefully you're kind of familiar with that. Just the idea of you can add, subtract, multiply, divide functions to each other. You can do the same thing with sine and cosine. If you're familiar with trigonometry because you've done that, you can do the same thing. But I'm going to move past this slide because, I mean, this is pretty straightforward. For one of them, you're just going to do sine squared x plus cotan x, and that's really all you can do to it. If you know your identities, you might be able to make this 1 minus cosine squared x plus cotan x. Or alternatively, you could do sine squared x plus cosine over sine. Then you could add an extra sine, cube that, and make it sine cubed x plus cosine all over sine. But hopefully you get the concept of how you can add, subtract, multiply, divide these guys. Hopefully that's not something new. When you get to questions on assignments about it, either you'll get it right away or you'll have to just shoot me an email. Ask me on Tuesday, Thursdays for questions about this. But I want to move on to the last topic, which is compositions of functions. This basically means that you're going to replace a function for a variable. You're going to take an entire thing and you're going to substitute. Hopefully you remember your substitution from like systems of equations in grade 10 and 11. The idea is you're going to take an entire function and place it inside another function. And there's two main ways of writing it. F bracket g bracket x or FOG bracket x. And the way it's read, if you want to read it out loud, this is pronounced F of g of x. That's how you would verbally say this thing. F of g of x. So let me show you how it works. Hopefully this is something you know. If not, then we're practicing. So this notation means f of g of x. And one of the ways I like to think of it is that you're really being asked to find f of g of x. And so the way I could write this is then, well, g of x is x plus 4, right? Like I'm literally saying that g of x is x plus 4. That's what this notation means. Well, this notation here is supposed to be, like f of x is supposed to be x squared. But rather than it being x squared, it's now going to be x plus 4 squared. Do you see how, hopefully you can see, how this is what I was given here. This is f of x is x squared. So if I ask you for f of g of x, which is what this notation here means, since g of x is x plus 4, I'm going to take this x right here and make it x plus 4. Which means this x plus here is also x plus 4. So kind of for your final answer then, you would say that f of g of x, which is equal to all of this stuff here, is x squared plus 8x plus 16. And that's considered a composite function, where we kind of took this x plus 4 and put it inside the x squared. So the x plus 4 has got put inside the x squared. So hopefully that's not brand new to you. Now that's one way of substituting, where I take this guy and I put it inside there. But I can go the other way, and that's what the other notation is. If I take this and put it inside there, let me show you that. G bracket f of x is what this notation means. It's g of f of x. So if g of x is supposed to be x, well, if f of x right here, this f of x is supposed to be x squared, if I do g of x squared, it was supposed to be x plus 4. Well, now it'll be x squared plus 4. This x really replaces this one right here. Right? If this is an x, well, now it's an x squared. Well, if this was an x, now this one's an x squared. So that's composite functions. Again, that's a major topic in 30-1. So it's unfortunate if you're doing this concurrently. I will try to give you, when these things come up where you're doing things at the same time, it's not ideal. I will try to give you more of a lesson if I need to, but I don't want to try to reteach all of 30-1 while I teach calculus. Obviously, that's just, we're never going to get through it. So, but do email me, ask me questions, get a hold of me over video conferencing, or if you're in my school, just come find me. Okay, so let's actually get to a question here. I actually skipped that on this one here. You've been asked to find the domain of these things here. And the first one here, the domain would have just been x as an element of the reals. Pretty much every x would have been valid in these ones right here. But I want to try this again with some things where not every x would be considered valid, so we can talk about the domain. And this should be our last example. So let's do this one. If I do f of g of x, which you could write as f of g of x, what you're really being asked to do is f of x minus 2, because g of x is x minus 2. So when you do this, this really means that you're doing 1 over x minus 2. It would have been 1 over x, but rather than x being there, you're taking x minus 2 and putting it in its location. Which means we have a number you can't use. If I ask you the domain is basically x as an element of the reals with the exception of x being 2. You can't use 2, right? Because hopefully you're aware of this, but if you try plugging in 2 on the bottom, it gives you a problem. However, there's actually one more issue. You also can't have it be 0. Up here, x couldn't have been 0 up here, so it can't be 0 down here either. So if you have something that becomes an issue in either the first function, the second one, or what they combine to, those are your issues. So here's how we might write this. You can have every number from negative infinity all the way up until 0, but you can't have 0. Then you can restart again with 0 and go up till 2. You just can't have 2. And then you restart again with 2 and you go up to positive infinity. And that would be your domain. Basically, this is a fancy way of saying you can go all the way up to 0, but you can't have 0. Start at 0 again, go up to 2. You can't have 2. Start at 2 and keep going. There's just 2 numbers you can't use. So, yeah, we kind of did come full circle in this little lesson here with this concept here. You do have to know this domain notation to know which inputs are valid. So, all right. Let's try another one. Again, one more time here. If I go too fast on videos, please go back, rewatch. Unlike in class where there's kind of a wait time where I can physically look at you and say, hey, do you get it? Should I do it again? I don't get that option here. So I would recommend have a list sitting nearby for you where you can have things to ask questions on. So you say, oh, I did not get topic 2, slide 7. Can we go over that? Make a list of places where I lose you. Rewatch the videos, obviously, and then on Tuesdays and Thursdays, when we can talk in person over video conferencing, then let's ask questions then. So, okay, let's do our last example. G of f of x means that we want the g function, but we're replacing the inside variable. Rather than writing x's, we're going to write 1 over x's everywhere. Well, since the g function happens to be x minus 2, it's now going to be 1 over x minus 2. Well, I mean, in case you're not aware what this graph looks like, this is going to be your standard reciprocal graph. But with the translation, now making so that it's down 2, so it's been shifted down 2 units. That's essentially what this graph is when we're done. So let's talk about the restrictions on the domain. In this part right here, x can't be 0 is essentially the one thing it can't be. In this guy right here, you can have anything you want for domain. And in this guy right here, it still was x can't be 0. So combine it all together, what can't you have? You can't have 0. So maybe the best way of writing it is you're going to go from negative infinity up till 0. Round bracket, because you don't get 0. Or you can start on the other side of 0 again, still don't get 0, and you get to go to positive infinity. Alternate ways of writing it include curly bracket x such that x is, let's see, less than 0 but greater than 0. X is an element of the reals or something. You can do something funky like that. Some people will just say x can't be 0. All of these kind of mean the same thing. I need you to be familiar with all the notations, though. So going back to our first slides, make sure you're familiar with all the different ways of writing domain and range. So be familiar with the interval notation, be familiar with set and number line notation, because they're all valid. So, okay, that concludes our second video. Like always, if you have questions, email me, or we'll talk on Tuesdays and Thursdays. Okay.